Hello there, and welcome to another gentle journey with deep sleep seas. Perhaps you've had a long day, or maybe you're simply the kind of person who finds comfort in drifting off to thoughts of distant oceans, rather than counting endless sheep. Either way, tonight's voyage is made just for you. Let your shoulders drop, your breathing slow, and your thoughts begin to soften like ice melting at the edges. Did you know that in the coldest reaches of our oceans, water doesn't simply freeze into solid blocks, but instead forms intricate crystals that dance and gather into shapes as delicate as flowers? Tonight we're drifting into the quiet world of sea ice, where frozen water tells stories of stillness and transformation. We'll explore how ice forms in gentle layers, how tiny creatures make their homes in channels of brine, and how these frozen landscapes shift with the seasons in rhythms older than memory. But before we jump in, if you enjoy learning about our oceans, you're welcome to let us know where you're tuning in from and what time it is for you. It's always fascinating to see how far our stories reach. And if these quiet ocean journeys help you unwind, you're always welcome to subscribe so you can drift off with us whenever you need. Now let your body grow a little heavier as we begin. In the far reaches of our planet, where the sun hangs low on the horizon for months at a time and darkness stretches across the water like a blanket, something remarkable happens. The ocean begins to freeze, but this is not the simple, straightforward freezing you might see in a winter pond or a glass of water left outside on a cold night. This is something far more intricate, far more beautiful in its complexity. This is the birth of sea ice, and it unfolds in stages as gentle and patient as falling snow. The ocean, you see, is not made of pure water. It carries salt dissolved throughout its depths, and this salt changes everything. While fresh water freezes at 0 degrees Celsius, seawater must cool to about -1.8 degrees before the first ice crystals appear. This difference may seem small, but it shapes entire frozen worlds. The salt doesn't want to be part of the ice. As the water cools and reaches that critical temperature, something extraordinary begins. The very first ice to form appears not as solid sheets but as tiny needle-like crystals called fragile. These delicate structures are only a few millimeters across, fragile and ephemeral, floating freely in the surface waters. If you could see them up close, you might think of snowflakes or star-shaped dendrites. Each one unique, each one a perfect expression of geometry emerging from chaos. But unlike snowflakes that fall through air, fragile crystals form directly in the water, suspended and drifting with the currents. They're made almost entirely of pure freshwater ice because as they form, they push the salt away, rejecting it back into the surrounding sea. This process, quiet and invisible to the naked eye, is the very beginning of sea ice. It's how the ocean starts to transition from liquid to solid, molecule by molecule, crystal by crystal. On calm nights when the air is frigid and the sea is still, these fragile crystals begin to accumulate on the surface, creating a layer that looks almost oily, like a thin sheen spreading across the water. This stage is called grease ice, named for its appearance. The water takes on a matte finish, no longer reflecting light the way open ocean does. Instead, it absorbs it, looking dark and soupy. If you were standing on the deck of a ship passing through these waters, you might see the sea lose its shimmer, becoming flat and viscous, as if the ocean itself were thickening into something between liquid and solid. Grease ice is a transitional state, neither fully water nor fully ice. It bends and flows with the movement of waves, but it also resists them slightly, dampening their motion. The fragile crystals within it are bonding together, coagulating into larger structures. In this stage, the ice is so thin and fragile that it offers almost no resistance to a ship's hull, parting easily and reforming behind. But give it time, give it cold, and the transformation continues. As temperatures drop further and the grease ice thickens, it solidifies into a thin, continuous sheet known as nillers. Nillers is elastic, bending with the gentle rise and fall of swells beneath it. In its earliest form, when it's less than 5 centimeters thick, it appears very dark, almost black, earning the name dark nillers. This darkness comes from the water below showing through the thin ice. But as it thickens beyond 5 centimeters, it lightens in color, becoming what's called light nillers. Now it's more substantial, still flexible, but with growing strength. Watch nillers long enough, and you'll see something fascinating. Light winds or currents push sheets of nillers around, and when they meet, they don't break. Instead, they slide over one another in a process called rafting. The edges lift and overlap, one sheet gliding atop its neighbor like shuffled cards. This rafting creates areas where the ice is double or even triple thickness, the first hints of the textured, layered structure that will define more mature sea ice. From above, rafted nillers creates patterns of interlocking fingers, a beautiful tessellation written by physics and temperature across the ocean's surface. But not all ice forms in calm conditions. When the sea is rough, when winds blow and waves churn, the story unfolds differently. The fissile crystals still form, and the grease ice still appears. But instead of consolidating into smooth nillers, the motion of the water works the ice into circular shapes. Waves roll beneath the forming ice, and wind hurls the crystals into accumulations. These grow into slushy disks called pancakes or pancake ice. Each pancake can range from 30 centimeters to 3 meters across, and they're remarkably distinctive. What makes pancake ice so recognizable are its raised rims. As the circular ice pieces jostle and bump against each other in the waves, slush and fissile ice pile up along their edges, creating a raised border all the way around. From a distance, a field of pancake ice looks like countless lily pads floating on dark water, each one edged in white, each one bumping gently against its neighbors. Up close, the detail is mesmerizing. The rims are uneven, built up layer by layer with each collision, and the surfaces may be slightly domed or textured where snow has begun to accumulate. Pancake ice forms in conditions of wave action and turbulence, environments where smooth ice sheets cannot yet establish themselves. The ocean is still too restless, the motion too constant, but the pancakes themselves are surprisingly robust. They can grow thicker over time, and under continued cold conditions, they eventually freeze together. When this happens, when dozens or hundreds of pancakes fuse into a single continuous surface, the result is a sheet of ice with a remarkably rough underside. All those individual pancakes, with their raised rims and irregular shapes, create a lumpy, textured bottom surface quite different from the smooth undersides of congelation ice that formed in calm waters. This difference matters. The texture of the ice's underside affects how water flows beneath it, how heat is exchanged, and even where marine life can find shelter and food, a rough underside offers more surface area, more nooks and crannies where algae can cling and small creatures can hide from predators. The story of how ice forms, whether in calm or in storm, shapes not just the ice itself but the entire ecosystem that will depend on it. As ice continues to grow, a new process takes over. Once a continuous surface has formed, whether from nillers or from fused pancakes, the open water below is insulated from the coldest air above. Now ice can no longer form from fissile crystals mixing in the water column. Instead, new ice grows downward from the bottom of the existing sheet. Water molecules freeze directly onto the underside in a process called congelation growth. This creates a very different crystal structure. While fissile crystals are small and randomly oriented, congelation ice forms long vertical crystals that grow slowly downward, parallel to each other, like the columns of a cathedral. This columnar structure gives the ice strength and stability. The crystals can grow to be many centimeters long, aligned in the same direction, creating an organized architecture. As the ice thickens through congelation growth, it can reach depths of 30 centimeters, then a meter, then more. First-year ice, ice that grows through a single winter and hasn't survived a summer melt, typically ranges from 30 centimeters to 2 meters thick, but the thickening slows as the ice grows deeper. The ice itself acts as insulation, making it harder for heat to escape from the water below to the air above. Eventually, growth nearly stops. The ice has reached a thickness where the rate of heat loss is so slow that no more freezing occurs, at least not through congelation. But ice can still thicken through other means. Snow can accumulate on top, and under pressure, it can compact and freeze into additional ice layers. In rough conditions, ice sheets can collide and pile up, forming pressure ridges that tower above the surrounding ice and extend deep keels beneath the surface. These processes add complexity and thickness, creating a frozen landscape of peaks and valleys, smooth plains and jagged ranges. The birth of sea ice is not a single moment but a cascade of transformations, each stage building on the last, each one shaped by temperature, wind, waves, and the patient chemistry of salt and water. Once sea ice has formed, it doesn't remain static. It ages, it changes, it responds to the seasons and to the forces that act upon it. The ice we see spread across polar oceans is not uniform. It's a mosaic of different types, each with its own characteristics, its own history written in structure and strength. Understanding these types is like learning to read the frozen sea, to see in its surface not just a sheet of white but a complex, living archive of time and temperature. Young ice is the term given to ice that has moved beyond nelas, but hasn't yet become first-year ice. It's the adolescent stage, ranging from 10 to 30 centimeters thick. This category is further divided into gray ice and gray-white ice. Gray ice is the thinner of the two, between 10 and 15 centimeters thick. It's called gray because it lacks the brightness of thicker ice. Light still penetrates it to some degree, showing the dark water beneath, giving it that characteristic gray tone. Gray ice is less elastic than nelas. It doesn't bend as easily with the waves. Instead, it tends to break, and under pressure from wind or currents, it's prone to rafting, sliding over itself in overlapping sheets. Gray-white ice is thicker, between 15 and 30 centimeters, and its color is lighter, closer to white. This ice has more structural integrity. When it encounters pressure, it's more likely to ridge than to raft. Ridging is a more dramatic process than rafting. Instead of smooth overlapping, ridging involves the ice breaking and piling up into chaotic heaps. Blocks of ice tumble over one another, creating a jumbled, hummocky surface that can rise several meters above the surrounding ice and extend even deeper below in structures called keels. These keels can plunge 10 or 20 meters beneath the surface, massive underwater mountains of broken ice held together by freezing and pressure. First-year ice is ice that has grown through one winter, but has not yet survived a summer. It's the most common type of sea ice in both the Arctic and Antarctic, though it behaves differently in each region due to local conditions. First-year ice varies widely in thickness, from 30 centimeters up to 2 meters or more, depending on how cold the winter was and how long the growing season lasted. It can be further categorized into thin first-year ice, medium first-year ice, and thick first-year ice, each with slightly different properties and behaviors. Thin first-year ice is between 30 and 70 centimeters thick. It's substantial enough to support some weight, but it's still relatively fragile. Medium first-year ice ranges from 70 to 120 centimeters, offering more stability. Thick first-year ice is anything over 120 centimeters. By the time ice reaches this thickness, it has developed considerable strength. It can support heavy loads, resist wave action, and provide a stable platform for animals to rest, hunt, and travel across. Polar bears walk on thick first-year ice. Seals haul out onto it. It becomes not just ice but habitat. But first-year ice, no matter how thick, faces a test. When summer arrives and temperatures rise, will it melt completely, or will some portion survive? In the Antarctic, almost all first-year ice melts away each summer. The ice is free to drift northward into warmer waters, and because there's no land boundary to constrain it, the vast majority disappears. But in the Arctic, particularly in the central Arctic Ocean, a significant portion of first-year ice survives the summer. It becomes second-year ice, and if it survives a second summer, it becomes multi-year ice. This distinction matters enormously. Multi-year ice is fundamentally different from first-year ice. It's thicker, typically ranging from 2 to 4 meters, though in some areas it can exceed that. It's also much less salty. During the summer melt, fresh water from melting snow and ice percolates down through the ice, flushing out brine and leaving the ice more like frozen freshwater than frozen seawater. This desalination makes multi-year ice harder, stronger, and less permeable. Its surface is often smoother in some places, worn by summers of melting and polishing by wind and rain. In other places, it's rougher, marked by the scars of years of pressure and collision. Multi-year ice can also be blue. Where the ice is thick and the bubbles have been compressed out, it takes on a beautiful deep blue hue, the same color you see in glacial ice. This blue ice is dense and hard, almost like stone. It's the ice that presents the greatest challenge to ships navigating polar waters. Icebreakers can push through first-year ice with relative ease, but multi-year ice resists. It's the old guard of the frozen ocean, the ice that has endured, that has been tested by summers and winters alike and remains. The distinction between fast ice and pack ice is one of mobility. Fast ice is ice that is attached to the shore or to the seafloor in shallow areas. It doesn't drift. It stays in place through the winter. anchored by its connection to land or grounded on shallow banks. Fast ice forms a stable platform extending out from coastlines, sometimes for kilometers. It's the ice that provides the most reliable habitat for species that need stable ground. The ice where Inuit and other Arctic peoples have traditionally hunted and traveled. Pack ice, by contrast, is free-floating. It drifts with winds and currents, constantly in motion. Most of the sea ice in the central Arctic Ocean and in the waters around Antarctica is pack ice. It moves in great slow gyres, circulating, compressing, spreading apart. Pack ice is dynamic, ever-changing. One day it may be compact, with ice floes pressed tightly together. The next, leads of open water may appear as the ice diverges, creating navigable channels through otherwise impassable fields. Within pack ice, ice floes are the individual pieces, and they vary dramatically in size. A small floe might be only a few meters across. A giant floe can extend for kilometers, a vast floating island of ice. These floes collide, break apart, freeze together, and break apart again in an endless cycle driven by the restlessness of the ocean and atmosphere. When floes collide under the force of strong winds or currents, pressure builds. The ice can't escape, so it has no choice but to deform. In some cases, this means rafting, with one floe riding up onto another. But more dramatically, it means the formation of pressure ridges. These are among the most striking features of the sea ice landscape. On the surface, a pressure ridge appears as a long, linear pile of ice blocks, sometimes rising 3 or 4 meters high, sometimes even more. The blocks are jumbled, angular, freshly broken. The ridge can extend for hundreds of meters or even kilometers, a barrier cutting across the otherwise flat expanse of ice. But the real scale of a pressure ridge is hidden below. For every meter the ridge rises above the ice surface, called the sail, there may be 4 or 5 meters extending below, called the keel. The keel is the ice's deep foundation, the massive underwater structure that balances the visible ridge above. Keels can extend 20 or 30 meters beneath the surface, creating obstacles and habitats in the water below the ice. Fish and seals navigate around them. Ocean currents swirl and eddy in their presence. The keel is a critical part of the ice's architecture, invisible from above but profoundly important to the physics of how ice behaves and how it interacts with the ocean. Between the ridges and the floes lie the level ice plains, areas that appear flat and smooth, covered perhaps with a layer of snow. These are the highways of the sea ice, the easiest routes for travel, the calmest surfaces. But even here, the ice is textured by history. Old refrozen leads create lines of thinner ice. Wind-sculpted snow forms dunes and sastrugi, wave-like patterns frozen in place. Melt ponds from previous summers leave depressions that fill with snow. Every feature tells a story of formation, deformation, melting, and refreezing. As ice ages from young to first year to multi-year, it accumulates these stories. Its surface becomes more complex, its structure more varied. The oldest ice in the Arctic, some of it more than 5 years old, is a palimpsest of summers and winters, each season adding layers of meaning, each weather event leaving its mark. This ice has traveled thousands of kilometers, drifting in the great Arctic gyres. It has pressed against coasts, squeezed through straits, spread across open basins. It carries the history of the frozen ocean in its very substance. And yet, for all its complexity, sea ice is ephemeral in the geological sense. Even multi-year ice, even the oldest ice, rarely persists more than a decade before it eventually melts or is crushed and broken. The ice we see today is not the ice of a century ago. It's newer, younger, more temporary than we often imagine. The frozen ocean is constantly renewing itself, constantly rewriting its own story in fresh ice, in new ridges, in the next generation of flows that will form when winter returns. To truly understand sea ice, you must imagine yourself shrinking down to microscopic size and venturing into its interior. If you could do this, if you could slip between the ice crystals and navigate the hidden passages within, you would discover a secret world unlike anything on the surface. This is the world of brine channels, and it's one of the most extraordinary features of sea ice. A place where physics and chemistry create conditions so extreme that it seems impossible for life to exist, and yet life not only exists but thrives. Remember that when seawater freezes, salt is rejected from the forming ice crystals. But that salt doesn't simply vanish. It can't disappear into thin air. Instead, it concentrates in pockets and channels of liquid brine that remain within the solid ice. These brine channels are tiny, often less than a millimeter in diameter, but they form an intricate three-dimensional network threading throughout the ice like the veins in a leaf or the passages in a sponge. Some are vertical, following the columnar structure of congelation ice crystals. Others branch and connect horizontally. Together, they create a labyrinth within the frozen matrix. The brine in these channels is not normal seawater. It's far saltier. While ocean water typically has a salinity of about 35 parts per thousand, the brine in newly formed sea ice can have salinities exceeding 100 parts per thousand, sometimes reaching 150 or even higher. This is 3 or 4 times saltier than the sea itself. Such extreme salinity has profound effects. Water with this much salt has a much lower freezing point. Even when the ice around it is well below 0 degrees Celsius, the brine remains liquid, a supercooled hypersaline solution trapped within a frozen world. But the brine channels are not static, they change with temperature. When the air above the ice cools, the ice itself cools, and the coldest temperatures are found at the top of the ice, while the bottom, in contact with seawater, remains near the freezing point of seawater. This creates a temperature gradient through the ice. At the surface, temperatures might be -30 or -40 degrees Celsius in the depths of winter, a meter below. At the bottom of the ice, it's only -2 degrees. This gradient shapes the brine channels. When temperatures drop, some of the water in the brine channels freezes, depositing pure ice on the channel walls and further concentrating the remaining brine. The channels may narrow or even close off entirely in the coldest ice near the surface. But as you go deeper into the ice where it's warmer, the channels are wider and more voluminous. This creates a dynamic, three-dimensional structure where some areas of the ice are permeated with brine and others are nearly pure ice with only tiny scattered pockets of liquid. As winter progresses and the ice thickens, gravity also plays a role. The dense, hypersaline brine is heavier than the seawater beneath the ice. So slowly, almost imperceptibly, brine begins to drain downward through the channel network. It seeps through the ice, finding pathways from channel to channel, moving from the interior of the ice toward the bottom, where it eventually drips into the ocean below. This process is called brine drainage or gravity drainage, and it's one of the primary ways that sea ice loses salt over time. Brine drainage is enhanced in the warmer months. In spring and summer, temperatures rise, and the ice warms throughout its thickness. The brine channels expand as ice along their walls melts, permeability increases, and in the Arctic, where snow and surface ice melt, fresh water percolates down into the ice, flushing through the brine channels and accelerating the desalination process. This is why multi-year ice is so much less salty than first-year ice. It has had multiple summers to flush out its salt, leaving behind an ice matrix that's closer to frozen fresh water. But in the coldest depths of winter, the brine channels present conditions that seem hostile to life. Temperatures well below freezing, salinity 3 or 4 times higher than seawater, darkness, because very little light penetrates thick ice and snow cover. Fluctuating conditions as temperatures change and channels narrow or widen. It's an environment of extremes, a place where most organisms would struggle to survive even briefly. And yet, the brine channels are inhabited. They are in fact teeming with life. Microscopic organisms have adapted to this harsh environment in ways that are nothing short of remarkable. Algae, bacteria, fungi, viruses, and tiny animals all make their homes in the brine channel network, forming a complex ecosystem known as the sympagic community, from the Greek words for together and ice. This is the ice-associated ecosystem, life that exists not just under the ice or on top of it, but within it. The structure of the brine channels is crucial to this ecosystem. The channels are connected, allowing exchange of nutrients and organisms. At the bottom of the ice, where the brine channels open into the seawater below, there's a steady flow of nutrient-rich water. Nutrients can be drawn up into the channels, fueling the growth of algae, and the channels themselves, while tiny to human eyes, are vast to the microorganisms that live within them. A brine channel half a millimeter wide is a highway, a feeding ground, a universe to a diatom that's only a few micrometers across. These organisms don't just tolerate the extreme conditions, they've evolved specifically for them. Ice algae, for instance, produce special compounds that protect them from the damaging effects of freezing and high salinity. Some secrete extracellular polymeric substances, sticky matrices that help them cling to the ice, and may also modify the local environment, perhaps making it slightly more hospitable. Others produce ice-binding proteins that prevent ice crystals from growing and damaging their cells. These adaptations allow algae to survive, and even to grow, in conditions that would kill most other photosynthetic organisms. The brine channels also have another remarkable property. Though they exist within solid ice, they're not isolated from the world outside. At the bottom of the ice, the brine channel network is open to the ocean. This creates a kind of interface where the solid and liquid worlds meet and exchange. Nutrients flow up into the channels. Organisms can move between the ice and the water, and when ice melts, either at the bottom during growth or throughout the ice during summer, the contents of the brine channels, including all the life they contain, are released back into the ocean. This connection between ice and ocean is vital. It means the brine channel ecosystem is not cut off, but is part of the larger marine ecosystem. It also means that sea ice plays a role in the ecology of polar oceans that goes far beyond simply being a physical barrier between air and water. The ice is habitat, and the organisms within it are a crucial link in the food web, providing food for larger zooplankton and fish, seeding blooms of phytoplankton when the ice melts, and contributing to the overall productivity of polar seas. In the Antarctic, where sea ice is mostly first year and melts extensively each summer, the release of ice algae and other organisms into the water can trigger massive blooms. The nutrients that have accumulated in the ice, the organisms that have grown within it, all of this is suddenly liberated when the ice disappears. The result can be explosions of life in the newly open water, blooms visible from space as the ocean turns green with chlorophyll. The brine channels are also responsive to seasonal changes in a very immediate way. In winter, they contract. The coldest, most saline, least hospitable conditions prevail. Life slows down. Many organisms enter dormant states, waiting for conditions to improve. But in spring, as temperatures rise and sunlight returns, the channels begin to warm. Ice along their walls melts, expanding the available space. Salinity decreases as fresh water mixes in, and critically, light begins to penetrate through the ice and snow. Photosynthesis becomes possible again. Algae wake from dormancy and begin to grow. They reproduce, their populations doubling and doubling again. The brine channels, which in winter might have held only a scattering of dormant cells, can become densely packed with life by late spring. The biomass of algae within sea ice can be astonishing, rivaling or even exceeding the density of phytoplankton in the water below. In some cases, the bottom few centimeters of sea ice can contain more than 1 billion algal cells per liter of brine, a concentration so high that the ice itself appears colored, taking on shades of brown, green, or gold from the pigments in the algae. This seasonal cycle, this rhythm of dormancy and bloom, of contraction and expansion, is driven by the same forces that govern the ice itself: temperature, light, and the interplay of fresh water and salt. The brine channels are not separate from the ice. They are an integral part of it, shaped by its physics and chemistry, but also shaping it in return through the activities of the organisms that live within. If the brine channels are the hidden architecture of sea ice, then the organisms that inhabit them are its secret inhabitants, the residents of a parallel world that exists just millimeters away from the open air, but might as well be on another planet for all the differences in environment. To understand life in the frozen sea, you must first appreciate just how small these organisms are, and how remarkably adapted they've become to conditions that would kill most other forms of life. The foundation of the sympagic ecosystem is algae. Among the most important are diatoms, single-celled photosynthetic organisms encased in intricate shells made of silica, the same material that forms glass. Diatoms are ubiquitous in the ocean, but the species found in sea ice are specialists. They have evolved to thrive in cold, to tolerate high salinity, and to make the most of the dim light that filters through ice and snow. Some sea ice diatoms are so abundant that they're responsible for more than half of the primary production in Arctic waters during spring and early summer, converting sunlight and carbon dioxide into organic matter that fuels the rest of the ecosystem. One of the most remarkable species is Melissaera arctica. a diatom that forms long filaments hanging down from the underside of the ice like delicate, translucent curtains. These filaments can extend several meters into the water column, swaying gently with the currents. Melisera creates its own habitat, building structure where there was none, and in doing so provides shelter and food for countless other organisms. Small crustaceans graze on the filaments. Juvenile fish hide among them. The filaments themselves are architectural wonders, each one composed of thousands of individual diatom cells stacked end to end, each cell protected by its glass shell, each contributing to the collective structure. Other ice algae are found not hanging beneath the ice, but living within the brine channels themselves. These species are even more remarkable in their adaptations. They must cope not only with the normal challenges of life in polar seas, but also with the confinement of the channels, the extreme salinity, the fluctuating temperatures, and the possibility that their liquid environment could freeze solid around them at any moment. To survive, these algae employ a range of biochemical strategies. They produce osmolytes, small organic molecules that help balance the osmotic pressure inside their cells with the high salinity outside. Without osmolytes, water would be sucked out of the cells by the concentrated brine, causing the cells to shrivel and die. With osmolytes, the cells can maintain their integrity even in brine several times saltier than normal seawater. They also produce cryoprotectants, substances that prevent ice from forming inside the cell or that bind to ice crystals and prevent them from growing. Some algae secrete extracellular polymeric substances that form a protective matrix around them, a kind of biological antifreeze that modifies the freezing behavior of the surrounding brine. These EPS compounds are sticky and gelatinous, and they may also serve to anchor the algae to the walls of the brine channels, preventing them from being flushed out when brine drains from the ice. In terms of light, ice algae face a peculiar challenge. The light levels within sea ice are very low, especially in winter and early spring. Thick ice, covered by snow, may transmit only 1 or 2% of the sunlight that hits the surface. At the bottom of the ice, where most algae are concentrated, light levels can be so dim that it's hard to imagine photosynthesis being possible at all. But ice algae have adapted to low light in several ways. They have high concentrations of photosynthetic pigments, allowing them to capture and use even the faintest illumination. They also grow best at the very bottom of the ice, where they're closest to the nutrient-rich seawater and where light, though dim, is slightly more available than higher up in the ice. But algae are not the only life in the brine channels. Bacteria are even more abundant, existing in densities that can reach billions of cells per liter. These bacteria perform a variety of roles. Some are decomposers, breaking down dead algae and other organic matter and recycling nutrients. Others are involved in nitrogen and sulfur cycling, transforming compounds in ways that make nutrients more available to algae. Still others may be parasites or symbiotes of the algae themselves, living in close association and influencing their health and growth. Viruses are also present in sea ice, sometimes in astonishing concentrations. In the ocean, viruses are the most abundant biological entities, and the same holds true in the brine channels. These viruses infect bacteria and algae, and they play a role in controlling the populations of their hosts. When a virus infects an algal cell and replicates, it eventually causes the cell to burst, releasing new viruses but also releasing the cell's contents, including dissolved organic matter and nutrients, back into the brine. This viral shunt, as it's called, is an important part of the nutrient cycle in sea ice, ensuring that nutrients locked up in living cells are made available to other organisms. Beyond the microbes, there are also larger organisms, though larger is relative. When you're talking about life in brine channels, tiny nematode worms, flatworms called turbellarians, and microscopic crustaceans like copepods can all be found in sea ice. These animals are small enough to navigate the brine channel network, and they feed on the algae and bacteria that grow there. Some spend their entire lives in the ice. Others are temporary residents, juveniles or larvae that use the ice as a nursery, feeding on the rich ice algae before eventually leaving to join the plankton in the water below. One group of crustaceans, the amphipods, deserves special mention. Some species of amphipods are closely associated with sea ice, living on its underside or within its matrix. These tiny creatures, often less than a centimeter long, are grazers and scavengers. They scrape algae from the bottom of the ice, crawl through crevices and brine channels, and are themselves an important food source for fish and seals. In some areas, amphipods can be so abundant that the underside of the ice seems to be alive with them, a writhing carpet of small bodies. The sympagic food web, the network of feeding relationships within and around sea ice, is complex and tightly linked to the broader marine ecosystem. At the base are the ice algae and bacteria, the primary producers and decomposers. Feeding on them are the tiny grazers, protozoans, small crustaceans, larvae. These in turn are eaten by larger zooplankton and small fish, and those are preyed upon by seals, whales, and seabirds. The productivity of sea ice, the life it supports within and beneath it, radiates outward and upward through the ecosystem, supporting species far removed from the ice itself. One of the reasons ice algae are so important is timing. In polar regions, the spring bloom of phytoplankton in the open ocean is one of the most productive events of the year, a time when sunlight returns, the water warms, and microscopic plants explode in growth, turning the sea green and feeding vast numbers of zooplankton. But the ice algae bloom happens earlier. While the ocean is still covered with ice and the water column is still cold and dark, the algae at the bottom of the ice have access to light and nutrients. They begin growing while phytoplankton in the water cannot. This means that ice algae provide an early source of food at a critical time for many species. For Arctic cod, a key fish species in the Arctic Ocean, ice algae and the zooplankton that feed on them are essential. The cod's life cycle is timed to take advantage of the ice algae bloom. For krill in the Antarctic, ice algae are a lifeline during winter and early spring, when other food is scarce. Krill can scrape algae from the underside of the ice, feeding on what's called the sea ice lawn, a dense mat of algae that forms in favorable conditions. The relationship between sea ice and krill is so important that fluctuations in sea ice extent can affect krill populations, which in turn affects everything that eats krill: penguins, seals, whales. The loss of sea ice in some regions has been linked to declines in krill, with cascading effects through the ecosystem. This illustrates a crucial point. Sea ice is not just ice, it's habitat, its food source, its nursery. It's a fundamental component of polar marine ecosystems and the life it supports, from the tiniest bacteria in brine channels to the largest whales feeding on krill. All depend on the existence and persistence of this frozen world. When sea ice melts in spring and summer, the organisms within it are released into the water. This seeding effect can trigger phytoplankton blooms in the newly ice-free areas. The algae that were growing in the ice now find themselves in open water with more light and space. They continue to grow, and their numbers can explode. The nutrients that were concentrated in the ice are also released, fertilizing the water. The result is a burst of productivity that supports the entire marine ecosystem during the brief polar summer. But this relationship is fragile. It depends on the ice forming at the right time, melting at the right time, and providing the right conditions for the organisms that live within it. Changes in the timing, extent, or thickness of sea ice can disrupt this delicate balance. If ice forms later or melts earlier, the algae bloom might be mistimed relative to the needs of grazers. If ice becomes thinner, more light might penetrate, which could sound beneficial but might also change the species composition or the timing of the bloom in ways that are hard to predict. The life within sea ice is a testament to the adaptability of organisms, to the ability of evolution to find solutions to even the most extreme challenges. In brine channels less than a millimeter wide, in darkness and cold and salt, life not only persists but flourishes. It's a hidden world, invisible from the surface, often overlooked even by scientists until recent decades. But it's a world of profound importance, a place where the physics of freezing water and the biology of adaptation meet to create something extraordinary. In the vast expanse of polar ice, where frozen seas stretch to the horizon in every direction, there are sometimes openings. Areas of open water or thin ice surrounded by thick ice pack, persisting even in the depths of winter when everything else is frozen solid. These are polinias, and they are among the most important features of the sea ice landscape, places where the normal rules seem suspended, where life concentrates, and where the ocean can breathe even when it's covered by ice. The word polynya comes from Russian, where it means a natural ice hole. Early explorers in polar regions sometimes mistook large polynyas for the open ocean, not realizing they were isolated openings within the ice. But polynyas are far from random occurrences. They form in specific places for specific reasons, and they play critical roles in ocean circulation, ice production, and ecosystem functioning. There are two main types of polynyores, distinguished by how they form. Latent heat polynyores, also called coastal polynyores, form when wind or ocean currents push ice away from a coastline or an ice shelf. As the ice is driven offshore, it leaves open water behind. This open water is exposed to the frigid air above, and new ice forms rapidly, freezing the surface. But the wind continues to blow, pushing the newly formed ice away as well, maintaining the open water. The cycle continues: freeze, push away, freeze again, push away again. The polynyore becomes a factory for ice production, churning out new ice that's constantly advected away from the opening. Latent heat polynyores are called that because the heat released during freezing, the latent heat of fusion, is what warms the air above the polynyore. When water freezes, it releases energy, and this energy is carried away by the cold wind. The polynyore is literally a place where the ocean is losing heat to the atmosphere at a tremendous rate, much faster than through existing ice, which acts as insulation. The other type of polynyore is the sensible heat polynyore, also called an open ocean polynyore. These form not by wind pushing ice away, but by warm water rising from depth. In certain locations, ocean circulation brings warmer water from below up to the surface. This water is still cold by any normal standard, but it's warm enough to melt ice from below or prevent ice from forming, even when air temperatures are well below freezing. Sensible heat polynyores can be enormous and can persist for years, though they're less common than coastal polynyores. One of the most famous and mysterious sensible heat polynyores is the Weddell polynyore, which appeared in the Weddell Sea off Antarctica in the mid-1970s and persisted for several winters before disappearing. It covered an area of hundreds of thousands of square kilometers, a vast hole in the ice in the middle of one of the coldest regions on Earth. Scientists struggled to understand how it could exist. Eventually they determined that it was caused by a combination of ocean circulation and the topography of the sea floor. A seamount called moored rise created conditions where deep, relatively warm water could upwell to the surface, keeping the polynyore open. The Weddell polynyore hasn't reappeared regularly since, though there have been smaller openings in recent years, raising questions about whether it might return or what its sporadic presence means for the region's climate and ocean circulation. Coastal polynyores are more predictable. They tend to form in the same places year after year because the geography and the prevailing winds don't change much. One of the largest and most productive is the North Water polynyore, located in northern Baffin Bay between Canada and Greenland. This polynyore forms each winter and spring, maintained by northward winds that push ice southward, and by ocean currents that flow through the narrow passage of Smith Sound. The North Water can cover an area of 85,000 square kilometers at its peak, a vast region of open or newly forming ice in the midst of the frozen Arctic. Polynyores like the North Water are critically important to wildlife because they provide access to open water and to the rich productivity that comes with ice formation. They attract large numbers of animals. Marine mammals that need to breathe air rely on polynyores during winter when the rest of the ice-covered ocean is inaccessible. Narwhals, belugas, and walruses congregate in and around polynyores. Polar bears hunt at the edges where seals come to breathe and rest. Seabirds nest nearby on cliffs and feed in the polynyore waters, diving for fish and zooplankton. Indigenous peoples have known about polynyores for centuries and have used them as hunting grounds. The Inuit name for polynyores is Sarvajwak, meaning the place where there is much upwelling, a reference to the biological productivity. These openings in the ice are not just geographical features, but cultural and economic resources. Places of abundance in an environment that can otherwise be harsh and unforgiving. From a biological perspective, polynyores are hotspots. The combination of open water, sunlight, and the nutrients brought up by ocean mixing creates conditions ideal for phytoplankton growth. Even in winter, when light is limited, polynyores can support higher productivity than the surrounding ice-covered waters. In spring and summer, polynyore blooms can be spectacular, visible from satellites as brilliant patches of green against the dark ocean. But polynyores are also important for another reason: ice production. Remember that coastal polynyores are constantly freezing and having the new ice pushed away. This process creates enormous quantities of ice. In fact, coastal polynyas in Antarctica are estimated to produce a significant fraction of all Antarctic sea ice, despite covering a relatively small area. The ice produced in polynyas is thin, first-year ice, but there's so much of it that the cumulative effect is substantial. And with all that ice production comes salt rejection. When ice forms, it expels brine into the water below. In polynyas where ice is forming rapidly and continuously, the amount of brine rejection is immense. This brine, being denser than the surrounding water, sinks. It flows down across the continental shelf and can cascade into the deep ocean, mixing with other water masses and contributing to the formation of deep and bottom waters. In Antarctica, several major coastal polynyas are key sites for the formation of Antarctic bottom water, the densest water mass in the global ocean. The Ross Sea polynya and polynyas along the coast of East Antarctica produce vast quantities of cold, salty water that sinks and flows northward along the ocean floor, eventually spreading throughout the world's oceans. This process is a critical component of the global thermohaline circulation, the great ocean conveyor belt that redistributes heat, salt, and nutrients around the planet. Without polynyas, this deep water formation would be much less efficient. The polynyas act as chimneys, venting cold, salty water into the depths. Changes in polynya activity, whether due to shifts in wind patterns or warming temperatures, could have far-reaching effects on ocean circulation and climate. This is one reason why scientists pay close attention to polynyas, monitoring their size, duration, and the ice production within them. The life cycle of a polynya is tied to the seasons, but the exact timing and behavior vary by location. Some polynyas are seasonal, appearing each winter and disappearing in summer. Others are perennial, persisting year-round, though their size may wax and wane. Some are small, just a few kilometers across. Others are vast, spanning tens of thousands of square kilometers. The edges of polynyas are dynamic zones. Ice is constantly forming in the open water and being pushed away by wind. This creates a gradient from open water at the center to thicker, more consolidated ice at the margins. Along these margins, leads and fractures form, creating a complex mosaic of ice types and thicknesses. These transitional zones are often where wildlife activity is highest, where algae grow most densely, and where the exchange between ice and ocean is most active. Polynyas also have a strong influence on local weather. Open water in winter allows heat to escape from the ocean to the atmosphere. The air above a polynya can be significantly warmer than the air above the surrounding ice, creating temperature gradients that drive local wind patterns. Fog and frost smoke, where vapor rising from the open water condenses into mist, are common sights above polynyas. These plumes of water vapor can rise high into the atmosphere, sometimes visible from great distances, like breath on a cold morning. In the Antarctic, katabatic winds, cold, dense air flowing down from the high ice sheet, are a primary driver of coastal polynyas. These winds can be fierce, exceeding hurricane strength, and they blow almost continuously in some areas, pushing ice away from the coast with relentless force. The combination of katabatic winds and the shape of the coastline determines where polynyas form and how large they become. Some regions of Antarctica have multiple polynyas forming in a chain along the coast, each one a site of intense ice production and deep water formation. The study of polynyas has been revolutionized by satellite observations. Microwave sensors can detect polynyas even in darkness and through clouds, providing daily images of their extent and evolution. This has allowed scientists to map polynyas globally, to track their variability from year to year, and to study how they respond to changes in climate and ocean conditions. What has emerged is a picture of a polynya system that is both remarkably stable in some ways, with polynyas recurring in the same places year after year, and highly variable in others, with significant differences in size and duration from one year to the next. As the climate warms and sea ice changes, polynyas are also changing. Some coastal polynyas are forming earlier or lasting longer. Some are expanding in size. These changes have implications for ice production, for deep water formation, and for the ecosystems that depend on polynyas. Understanding these changes and predicting how they will continue is an active area of research, one that combines oceanography, atmospheric science, biology, and glaciology. Polynyas are windows in the ice, but they're also much more. They're engines of ice production, sites of deep water formation, oases of biological productivity, and cultural landmarks for the people who live near them. They're places where the solid and liquid worlds meet, where exchange is constant, where the ocean's influence reaches through the ice to the atmosphere above. In the quiet, frozen expanse of polar seas, polynyas are anything but quiet. They're places of motion, of transformation, of life. The polar regions, Arctic and Antarctic, are often spoken of together as if they're mirror images, northern and southern versions of the same frozen realm. But this pairing obscures profound differences. The Arctic and Antarctic are in many ways opposites, and nowhere is this more apparent than in their sea ice. To understand sea ice, you must understand that there are really two frozen oceans, each with its own character, its own rhythms, its own story. The Arctic is an ocean surrounded by land. The Arctic Ocean sits at the top of the world, hemmed in by the northern coasts of North America, Europe, and Asia. This geography shapes everything about Arctic sea ice. The ice is, to a large degree, landlocked. It can't drift freely in all directions. Instead, it circulates within the Arctic basin, moved by winds and currents in great slow gyres. Some ice is pushed against coastlines, piling up and thickening. Some is squeezed through narrow passages, like the Fram Strait between Greenland and Svalbard, where it escapes the Arctic and drifts south into the Atlantic. Because the ice is constrained, it tends to pile up and thicken. When ice flows converge, they can't simply spread apart elsewhere. They collide, and the result is rafting and ridging. Arctic ice is on average thicker than Antarctic ice. Multi-year ice, ice that has survived at least one summer, is common in the central Arctic Ocean. Some ice is 5 years old or more, thick and hard, sculpted by years of freezing, melting, and deformation. The Antarctic, by contrast, is land surrounded by ocean. Antarctica is a continent, a vast ice sheet sitting at the bottom of the world, and around it lies the Southern Ocean, unbroken by land, except for a few scattered islands. Sea ice forms around the edge of this continent and then drifts northward into open water. There are no barriers to constrain it. It can spread freely, and it does, expanding each winter to cover an area larger than the Arctic Ocean's ice cover. But because it drifts into warmer waters, and because there's no land to trap it, almost all Antarctic sea ice melts each summer. Multi-year ice is rare. The vast majority is first-year ice, thinner and more seasonal than its Arctic counterpart. This difference in geography leads to differences in thickness. Arctic ice averages 2 to 3 meters thick, with multi-year ice reaching 3 to 4 meters or more. Antarctic ice averages only about half a meter to a meter, though it can be thicker in places. The difference is stark. If you were to walk on Arctic ice in winter, you'd be on a thick, stable platform that could support heavy equipment, buildings, even runways for aircraft. If you walked on Antarctic ice, you'd be on a thinner, more fragile surface, still strong enough to support a person, but less substantial. The seasonal cycles also differ. In the Arctic, sea ice reaches its maximum extent in March, covering about 14 or 15 million square kilometers. It reaches its minimum in September, when it shrunk to about 4 or 5 million square kilometers in recent years, though this has been decreasing. About half the Arctic Ocean's ice melts each summer, and about half persists. This means there's always some ice present year-round, though the amount has been declining over recent decades. In the Antarctic, sea ice reaches its maximum extent in September, the end of the austral winter, covering about 18 million square kilometers, a larger area than the Arctic's maximum. But by February, the end of austral summer, it's shrunk to only about 2 or 3 million square kilometers. The vast majority melts away. The seasonal swing is enormous, far larger than in the Arctic. The Antarctic ice cover is highly dynamic, expanding and contracting across a range of more than 15 million square kilometers each year. These differences affect how the ice behaves and how it influences the ocean and atmosphere. Arctic ice, being thicker and more persistent, acts as a more effective insulator between ocean and air. It limits heat exchange, keeps the ocean colder, and reflects more sunlight back to space. Antarctic ice, being thinner and more seasonal, is less effective as an insulator, but covers a larger area at its maximum, influencing a vast expanse of ocean. The winds and currents that drive sea ice motion also differ between the two poles. In the Arctic, ice circulates in two main patterns: the Beaufort gyre, a clockwise circulation in the western Arctic, and the transpolar drift, which carries ice from the Siberian coast across the pole toward the Fram Strait. These patterns move ice slowly, over years, allowing it to thicken and age. In the Antarctic, the dominant pattern is the Antarctic circumpolar current, which flows endlessly eastward around the continent, and the Ekman transport driven by easterly winds near the coast, which pushes ice northward away from Antarctic. The result is a radial flow, with ice forming near the coast and drifting outward in all directions. The presence or absence of land also affects ice-ocean interactions. In the Arctic, land-fast ice is common, ice attached to the shore that doesn't move. This fast ice can extend for kilometers offshore, providing stable habitat and serving as a barrier that protects coastlines from wave erosion. In the Antarctic, land-fast ice exists but is less extensive because the coast is often steep and icy, with ice shelves extending over the water rather than shallow bays and beaches. Ice shelves are another key difference. Antarctica has massive ice shelves, thick platforms of glacial ice floating on the ocean. The largest, the Ross Ice Shelf, and the Filchner-Ronne Ice Shelf, each cover areas larger than many countries. These ice shelves influence sea ice formation and movement. Sea ice forms in the lee of ice shelves, and the shelves themselves can buttress sea ice, preventing it from drifting away. The Arctic has a few small ice shelves, but nothing comparable to Antarctica's giants. Biology also differs between the two poles. The Arctic has polar bears, walruses, Arctic foxes, and human communities that have lived on and around sea ice for thousands of years. The Antarctic has penguins, seals, and whales, but no permanent human inhabitants and no land-based predators. The marine ecosystems under the ice are different, too, with different species of fish, zooplankton, and algae adapted to the unique conditions of each pole. Climate change is affecting the two poles differently. The Arctic is warming faster than almost any other region on Earth, a phenomenon known as Arctic amplification. Sea ice extent has been declining dramatically, particularly in summer. The September minimum has decreased by about 40% since satellite records began in the late 1970s. The ice is also getting younger and thinner, with less multi-year ice and more first-year ice. This has profound implications for the Arctic climate, ecosystems, and for global weather patterns. The Antarctic, by contrast, showed a more complex pattern until recently. From the late 1970s through the early 2010s, Antarctic sea ice extent actually increased slightly overall, though with strong regional variation. Some areas lost ice while others gained it. This was puzzling and led to much scientific debate. But starting around 2016, Antarctic sea ice began a sharp decline, reaching record lows in recent years. The reasons are still being investigated, but changes in winds, ocean currents, and the influence of warming on ice shelves are all thought to play a role. These regional differences highlight an important point. Sea ice is not a simple, globally uniform phenomenon. It responds to local conditions, to geography, to ocean circulation, to atmospheric patterns. Understanding sea ice requires understanding each region on its own terms, recognizing that what happens in the Arctic may be very different from what happens in the Antarctic, even though both involve frozen seawater at high latitudes. The future of sea ice in both poles is uncertain, but projections suggest continued decline, particularly in the Arctic. Some models predict that the Arctic could be nearly ice-free in summer by mid-century or even earlier. What ice-free means in this context is that there would be less than 1 million square kilometers of ice, not literally zero ice, but a dramatic reduction from historical norms. Such a change would have cascading effects on Arctic ecosystems, on global ocean circulation, on weather patterns in temperate latitudes, and on the climate system as a whole. In the Antarctic, the future is harder to predict. The continent is more isolated, its climate more extreme, and the interactions between ice, ocean, and atmosphere more complex. But the recent rapid declines in sea ice extent are concerning and suggest that even the Antarctic, long thought to be more stable, is changing in response to a warming world. Sea ice lives by the seasons. Its entire existence is defined by the annual cycle of growth and decay, freezing and melting, expansion and retreat. This rhythm is as old as the polar regions themselves, a pulse that has beat for millennia, shaping ecosystems, influencing climate, and creating patterns that ripple through the Earth system. To understand sea ice is to understand this cycle, to appreciate the quiet inevitability of winter's advance and summer's retreat. In the Arctic, the cycle begins in September. This is when the ice reaches its minimum extent, when summer has melted away as much as it's going to melt. The ice that remains is a remnant, the survivors, mostly multi-year ice that has proven its resilience. The ocean around the ice is cold, but not yet freezing. Sunlight still reaches the surface for a few hours each day, though the days are growing shorter. The balance is about to tip. As September turns to October, temperatures drop. The sun dips below the horizon for longer periods each day, and eventually, in the high Arctic, it doesn't rise at all. Polar night begins, a period of continuous darkness that will last for months. Without sunlight, the ocean loses heat to the atmosphere and space. The surface water cools to the freezing point, and the first fossil crystals form. The ice begins to grow. At first, the growth is rapid. Open water freezes quickly, forming nelas and young ice. The ice expands outward from the edges of the existing ice pack, creeping southward, spreading across areas that were open ocean just weeks before. By November, the Arctic is transforming into a frozen sea. By December, vast areas are covered, and the ice continues to thicken as congelation growth adds layer upon layer to the underside of the existing ice. The coldest months are January and February. Now the ice is at its most hostile, its most extreme. Temperatures can plunge to -40 or even -50 degrees Celsius. The ice thickens to its maximum. Brine channels contract. Snow accumulates on the surface, insulating the ice and slowing further growth, but also adding to the total thickness. This is the depth of Arctic winter, when the frozen ocean is at its most solid, its most expansive. But even in the deepest cold, there are signs of the coming change. Daylight begins to return in late February. First just a glow on the horizon, then the sun's edge, then longer and longer periods of light. By March, the Arctic is bathed in sunlight again, though the temperatures are still well below freezing. The ice reaches its maximum extent in March, covering its largest area of the year. This is the peak, the moment of greatest frozen expanse, and from here, the cycle turns toward melting. April and May are the transition months. Temperatures rise, but the ice is still thick and solid. Sunlight, now abundant, begins to penetrate the snow and ice. Algae in the brine channels and at the bottom of the ice start to grow. The ice, which has been dormant and lifeless through winter, awakens. This is the season of the ice, algae bloom, when the frozen sea becomes a garden. By June, melting has begun in earnest. Melt ponds form on the surface where snow has melted and water has pooled in depressions. These ponds are darker than ice, absorbing more sunlight, which accelerates melting in a feedback loop. The ice begins to thin from above and below as the sun warms the surface and the ocean warms from beneath. Leads open up, cracks in the ice that reveal dark water. July and August are the height of the melt season. Temperatures are above freezing, sometimes well above. The ice edge retreats rapidly, pulling back northward, uncovering vast areas of ocean. Ice floes break apart and drift. Multi-year ice that has survived many summers now faces its test again. Some will make it through, some will not. The ice becomes fragmented, a mosaic of flows separated by widening gaps of open water. By September, the cycle has come full circle. The ice has reached its minimum, and the ocean, though cold, is absorbing sunlight and storing heat. But the days are growing shorter again. Freeze-up is approaching. The cycle will begin anew. In the Antarctic, the cycle is reversed. The seasons are opposite because Antarctica is in the southern hemisphere, so winter occurs when the Arctic has summer. But there's also a key difference. The Antarctic cycle is more extreme in its seasonal variation. In February, the end of Austral summer, Antarctic sea ice is at its minimum, covering only a few million square kilometers. Most of the Southern Ocean around Antarctica is open water, blue and relatively warm. The ice that remains is concentrated in a few areas, like the Weddell and Ross Seas. But as March arrives and autumn begins, the ocean starts to freeze. The freeze-up in the Antarctic is faster and more extensive than in the Arctic. Ice spreads rapidly outward from the continent, driven by cold temperatures and by the winds that push newly formed ice away from the coast. By May, the ice has expanded dramatically. By September, it covers an area larger than the Arctic's maximum, a vast frozen expanse encircling the entire continent. The Antarctic winter is dark and cold, but the ice is thinner than Arctic ice. It's mostly first-year ice, and much of it is constantly in motion, drifting northward into warmer waters. Polynyas form along the coast. producing ice that's immediately advected away. The ice cover is dynamic, always forming, always moving, never stable in the way Arctic ice can be. Spring arrives in October and November, and the melt is rapid. By December, large areas are already ice-free. By February, the ice has retreated back to the continent, and the cycle begins again. This rapid expansion and contraction, this extreme seasonality, is one of the defining features of Antarctic sea ice. The seasonal cycle affects everything. Wildlife times its life cycles to the ice. Penguins breed on the continent and feed in the ocean along the ice edge. Seals haul out on ice floes. Whales migrate to polar waters in summer to feed on the rich blooms that follow ice melt. Humans who work in polar regions plan their activities around the ice, traveling and conducting research during the brief summer when access is possible, hunkering down or leaving during the dark, frozen winter. The cycle also influences global climate. As ice expands in winter, it reflects sunlight back to space, cooling the planet. As it melts in summer, it exposes dark ocean water that absorbs heat, warming the planet. The seasonal pulse of ice growth and decay is one of the heartbeat rhythms of the Earth's climate system. But this cycle is not fixed. It varies from year to year, sometimes significantly. Some winters are colder, and ice expands further. Some summers are warmer, and ice retreats more. These variations are driven by natural variability in atmospheric and ocean circulation, El Niño and La Niña, the North Atlantic Oscillation, the Southern Annular Mode. All these large-scale climate patterns influence sea ice on timescales of months to years. And over longer timescales, the cycle is changing. The average summer minimum in the Arctic has been declining. The winter maximum has also been declining, though less dramatically. The ice is melting earlier in spring and freezing later in autumn, shortening the ice season and lengthening the open water season. These changes are most pronounced in the Arctic, where warming has been strongest, but they're beginning to appear in parts of the Antarctic as well. The seasonal rhythm of sea ice, which has been so reliable for so long, is shifting. The changes are subtle year to year, but over decades, the pattern is clear. The frozen ocean is not as frozen as it used to be. The seasons are changing, and with them the ice. Sea ice is far more than frozen water on the ocean's surface. It's an active participant in the Earth's climate system, influencing and being influenced by the atmosphere, the ocean, and the global flow of energy. To understand the role of sea ice in climate, you need to see it not as a static feature, but as part of a complex web of feedbacks and connections that extend far beyond the polar regions. One of the most important ways sea ice influences climate is through its effect on the planet's albedo, its reflectivity. Fresh snow on sea ice can reflect up to 90% of the sunlight that hits it, bouncing that energy back to space before it can warm the Earth. Even bare ice reflects 60 to 70%. This high reflectivity means that ice-covered regions stay cold. The ice reflects away the sun's energy, preventing warming, which keeps the ice frozen, which keeps the albedo high, a reinforcing cycle that helps maintain polar climates. But when ice melts and exposes open ocean, the albedo drops dramatically. Ocean water reflects only about 6% of sunlight, absorbing the rest. That absorbed energy warms the water, which makes it even less likely that ice will form, which keeps the albedo low. This is the ice albedo feedback, one of the most powerful positive feedbacks in the climate system. It amplifies warming. As ice melts, more heat is absorbed, which causes more melting, which absorbs more heat. In the Arctic, this feedback is a major reason why the region is warming faster than the global average. Sea ice also affects climate by insulating the ocean from the atmosphere. In winter, the Arctic Ocean is warmer than the air above it. If the ocean were exposed, it would lose enormous amounts of heat to the atmosphere through evaporation and direct heat transfer. But sea ice acts as a lid, a thermal barrier that slows this heat loss. The thicker the ice, the more effective the insulation. This keeps the Arctic Ocean warmer than it would otherwise be and keeps the Arctic atmosphere colder. When ice thins or disappears, more heat escapes from the ocean to the atmosphere. This can have far-reaching effects. The warmed Arctic atmosphere can influence weather patterns in temperate latitudes, possibly affecting the jet stream and storm tracks. Some scientists have proposed that the loss of Arctic sea ice is linked to changes in winter weather patterns in North America, Europe, and Asia, though this connection is still being researched and debated. Sea ice is also crucial to ocean circulation. Remember that when ice forms, it rejects salt, creating dense brine that sinks. This process occurs throughout the ice-covered polar oceans, but it's especially important in polynyas and other areas of active ice formation. The sinking brine drives vertical mixing in the ocean, bringing nutrients to the surface and carrying oxygen to depth. This mixing is part of what makes polar oceans so productive. On a larger scale, the dense water formed by sea ice production is a key component of the global thermohaline circulation, the system of currents driven by differences in temperature and salinity that transports heat, salt, and nutrients around the world. In the North Atlantic, cold, salty water formed in the Arctic and subarctic sinks and flows south along the ocean floor, forming North Atlantic deep water. In the Southern Ocean, Antarctic bottom water, the densest water in the world ocean, is formed through the same process of sea ice production and brine rejection. This water sinks to the ocean floor and flows northward into all the major ocean basins, eventually reaching even the North Pacific. These deep currents are the lower limb of the ocean's conveyor belt. They balance the upper limb, the warm surface currents that flow toward the poles, like the Gulf Stream in the Atlantic and the Kuroshio in the Pacific. Together, these currents redistribute heat on a planetary scale, carrying warmth from the tropics toward the poles and cold from the poles toward the tropics. The ocean is in effect a giant heat engine, and sea ice production is one of the key processes that keeps this engine running. Changes in sea ice could affect this circulation. If ice production decreases because less ice is forming, or if ice melts and adds fresh water to the surface ocean without the corresponding salt rejection, the formation of dense water could slow. This would weaken the thermohaline circulation, with potential consequences for climate worldwide. Some models suggest that continued warming and ice loss could lead to a slowdown of the Atlantic meridional overturning circulation, the system of currents that includes the Gulf Stream. Such a slowdown could cool parts of Europe and eastern North America even as the globe as a whole warms. Sea ice also interacts with the atmosphere in more direct ways. Ice-covered oceans exchange very little moisture with the air because the ice prevents evaporation. But when ice melts and exposes open water, evaporation increases, adding moisture to the atmosphere. This can lead to more clouds and precipitation. In the Arctic, the loss of sea ice has been linked to increased snowfall in some regions, which might seem counterintuitive, but is a result of the greater availability of moisture from the newly ice-free ocean. The roughness of the ice surface also affects atmospheric circulation. Smooth ice offers less resistance to wind than rough, ridged ice. Changes in ice roughness, perhaps due to changes in the age and thickness of the ice, can alter how wind flows over the Arctic Ocean, potentially influencing weather patterns. Sea ice is also a sink for carbon dioxide. When ice forms, bubbles of air are trapped within it. Some of this air, including CO2, can be incorporated into the ice structure or dissolved in the brine channels. When the ice melts, the CO2 is released. But during the time the ice exists, it represents a small amount of carbon temporarily sequestered. More importantly, the algae that grow in and under sea ice take up CO2 through photosynthesis, converting it into organic matter. Some of this organic matter sinks when the algae die or are eaten, and their waste products sink, transporting carbon to the deep ocean where it can be stored for centuries. Sea ice ecosystems, particularly the productive ice algae blooms, contribute to the biological carbon pump. Climate change is altering sea ice in ways that are still being studied and understood. The Arctic has lost a significant fraction of its summer ice, and the remaining ice is younger and thinner. This makes it more vulnerable to further melting. The ice albedo feedback is accelerating warming in the Arctic. The loss of insulation is warming the Arctic atmosphere. The changes in ocean stratification and circulation are affecting ecosystems and possibly global climate. In the Antarctic, the picture is more complex, but recent rapid declines in sea ice suggest that changes are underway there as well. The implications are not fully understood, but they could include changes in the formation of Antarctic bottom water, shifts in the Southern Ocean ecosystem, and effects on ice shelves and glaciers. The relationship between sea ice and climate is bidirectional. Climate affects ice through changes in temperature, winds, ocean currents, and precipitation. Ice affects climate through albedo, insulation, ocean circulation, and ecosystem processes. This two-way interaction means that sea ice is both an indicator of climate change and an active participant in it. Understanding this role is essential to understanding the Earth's climate as a whole. In our journey through the frozen seas, we've explored what we can see and what we can imagine: the crystals, the channels, the organisms, the vast expanses of white. But there's another dimension to sea ice that often goes unnoticed, another way to understand this frozen world. Sea ice makes sound. It speaks in a language of cracks and groans, pops and rumbles, a symphony of physics and pressure that echoes through the water and the air above. If you were standing on the Arctic ice on a cold, still day, you might hear it. A sharp crack, like a gunshot, sudden and startling, then silence, then another crack, distant this time, muffled by distance. These are the sounds of ice under stress, ice responding to temperature changes, to tidal forces, to the endless subtle movements of the ocean beneath. Ice, for all its appearance of solidity and stillness, is never truly still. It's always flexing, always adjusting, always responding to forces both large and small. The cracks come from thermal stress. As temperatures drop rapidly, the surface of the ice contracts, cooling and shrinking. But the ice beneath is warmer and doesn't contract as quickly. This difference in expansion and contraction creates tension within the ice sheet. Eventually, the tension exceeds the ice's strength, and it fractures. A crack opens, racing across the surface at tremendous speed, sometimes for hundreds of meters, sometimes for just a few. The sound is the release of stored energy, like the snap of a breaking stick, but amplified across tons of ice. Sometimes the cracks are small, hairline fractures visible only up close. Other times they're dramatic, opening leads several meters wide, dark water suddenly exposed to frigid air. These leads are important. They release pressure within the ice pack. They provide breathing holes for seals and whales. They're where new ice forms most rapidly, the fossil crystals appearing almost instantly on the newly exposed water. But cracking is just one voice in the ice's acoustic repertoire. There's also the sound of ice rubbing against itself, a low grinding or scraping that can last for hours. This happens when ice floes converge, pushed together by wind or currents. The edges of the floes meet and press against each other. At first, there might be just a gentle contact, a quiet friction, but as the pressure builds, the sound grows. The ice grinds and groans, the floes pushing, neither willing to give way. Eventually, one floe will ride up over the other in rafting, or the ice will buckle and break, forming ridges. These moments of deformation are accompanied by loud reports, crashes, and rumbles that can be heard for kilometers across the ice. Underwater, the ice makes different sounds. Seals and other marine mammals live in a world defined by acoustics. Water is a far better conductor of sound than air, and sounds travel faster and farther through the ocean than through the atmosphere. The noise of ice breaking, ridging, and moving creates an underwater soundscape that's constantly changing. Some sounds are high-pitched and sharp, like the tinkle of ice crystals forming in supercooled water. Others are low-frequency rumbles, the bass notes of large floes colliding, or the slow grinding of multi-year ice deforming under pressure. Marine mammals use sound to navigate, to communicate, to find food. The sounds of the ice are part of their environment, signals they must interpret and navigate around. Some sounds indicate danger, a large crack opening, a collapse of ice that might trap an animal underwater. Other sounds are neutral or even beneficial, marking areas of open water or thin ice where breathing is possible. Human ears, too, have heard the ice. Early Arctic explorers wrote about the eerie sounds of the ice, describing nights when the ice seemed to be alive with noise, groaning and creaking like a wooden ship under strain. These sounds could be unsettling, especially in the polar darkness when the source of the noise was invisible. But they were also a reminder of the ice's dynamism, of the forces at work beneath the surface. Modern technology has allowed scientists to study the acoustic properties of sea ice in detail. Hydrophones placed beneath the ice record the underwater soundscape. These recordings reveal a world far noisier than one might expect. There's the sound of waves breaking ice apart at the ice edge. There's the sound of snow accumulating on the surface, a soft patter and rustle amplified when heard from below. There's even the sound of brine draining through the ice, a faint trickling that can be detected with sensitive instruments. One of the most distinctive sounds is the ice's response to tidal motion. In areas where tides are significant, the rise and fall of the water level creates stress in ice that's grounded or attached to the shore. As the tide rises, The ice lifts and flexes. As it falls, the ice settles back down. This movement can create regular, rhythmic sounds, a kind of tidal breathing that matches the pulse of the ocean beneath. Temperature changes also create sounds in predictable patterns. During the day, when sunlight warms the surface, the ice may expand slightly and sounds decrease. At night, when temperatures plummet, the ice contracts and cracks multiply. In the depths of winter, during the coldest hours before dawn, the ice can be particularly active acoustically, a chorus of snaps and pops echoing across the frozen expanse. Wind, too, plays a role. Strong winds create pressure in the ice pack, pushing floes together in some areas and pulling them apart in others. The ice responds with creaks and groans, the soundtrack of wind-driven motion. When wind blows snow across the surface, the sound of billions of ice crystals tumbling and sliding creates a hiss, a whisper that can rise to a roar in blizzards. And then there are the sounds of life. Seals vocalize under the ice, their calls ranging from chirps and trills to deep, resonant tones. These vocalizations serve many purposes, attracting mates, defending territories, communicating between mothers and pups. The ice itself can affect how these sounds propagate. In some cases, it channels sound, focusing it and allowing it to travel farther. In others, it scatters sound, creating echoes and reverberations. Whales navigating ice-covered waters also produce sounds, using echolocation to find leads and openings. The clicks and whistles of belugas, narwhals, and bowhead whales are part of the acoustic environment. So are the more distant low-frequency calls of larger whales like fin and blue whales, sounds that can travel across entire ocean basins, passing beneath the ice and through the water column. Humans have added their own sounds to the mix. Icebreakers crushing through ice create a tremendous cacophony, the roar of engines combined with the crash and splinter of ice being broken. Research stations on the ice operate machinery, generators, and vehicles, all contributing to the soundscape. Even scientists walking on the ice, drilling cores or setting up equipment add small notes to the acoustic environment. But perhaps the most poignant sounds are those of ice melting. In spring and summer, as temperatures rise, the ice begins to disintegrate. Melt ponds form on the surface, and water trickles through cracks and channels. Ice crystals detach and fall, creating tiny splashes. The surface becomes porous, and in some areas the ice develops a honeycomb structure, fragile and collapsing. The sound of melting ice is a kind of soft dissolution, a gentle giving way that contrasts with the sharp violence of cracking and breaking. When ice floes break apart in waves, when icebergs calve from glaciers and crash into the sea, the sounds can be spectacular. These are not quiet events. The roar of falling ice, the splash of massive fragments hitting water, the subsequent waves and echoes, all of this creates a temporary but intense acoustic signature. Such events are rare, but when they occur, they're unforgettable. The soundscape of sea ice is not just a curiosity, it's a subject of scientific study. Researchers use acoustic monitoring to track the behavior of ice, to understand how it moves and deforms, to predict where leads will open or ridges will form. Changes in the ice's acoustic properties can indicate changes in thickness, salinity, or temperature. Sound is a diagnostic tool, a way to see into the ice without physically disturbing it. And as the climate changes and sea ice declines, the soundscape is changing too. Less ice means fewer cracks, less grinding, less of the deep winter chorus. But it also means more open water, more wind-driven waves, more rain falling on ice and water. The acoustic environment of the Arctic and Antarctic is shifting, and scientists are documenting these changes, using sound as one more way to track the transformation of the polar regions. For those who listen, ice tells stories. It speaks of cold and pressure, of motion and stillness, of the delicate balance between solid and liquid. It's a voice from a world that seems silent to human ears most of the time, but is in truth full of sound, full of expression, full of the constant conversation between ice and ocean, ice and atmosphere, ice and life. Looking forward, the future of sea ice is one of the most pressing questions in climate science. What will the polar oceans look like in 10 years? In 50? In a century? The answers are uncertain, but the trajectory is clear. Sea ice is declining, and that decline is accelerating in many regions. Understanding what this means requires looking not just at the ice itself, but at the web of connections it's part of, the systems it influences, and the lives, human and otherwise, that depend on it. In the Arctic, projections suggest that summer sea ice could decline to near zero levels by mid-century under many climate scenarios. Near zero doesn't mean the Arctic Ocean will be completely ice-free. Some ice will likely remain in the coldest regions near the pole and along the northern coasts of Greenland and the Canadian archipelago. But the vast expanses of summer ice that once characterized the Arctic could be gone, replaced by open water dotted with scattered floes and fragments. This would represent a fundamental transformation of the Arctic environment. The loss of summer ice would open new shipping routes across the top of the world, routes like the Northwest Passage and the Northern Sea Route that have been impassable through most of history. These routes could cut thousands of kilometers off shipping distances between Europe, Asia, and North America, with significant economic implications. But they would also bring risks: increased ship traffic in fragile ecosystems, the possibility of accidents in remote waters, and the introduction of pollutants and invasive species to regions that have been relatively isolated. The loss of ice would also affect Arctic ecosystems profoundly. Species that depend on ice, polar bears, ringed seals, walruses, ice-associated algae, would face challenges. Polar bears hunt seals from ice platforms, and without ice, their ability to find food diminishes. Some populations are already showing signs of stress, with lower body weights and reduced reproductive success. Walruses use ice floes as resting platforms between feeding dives, and without ice, they must haul out on land, creating overcrowded conditions that can lead to trampling and increased vulnerability to predators. For ice algae and the ecosystems they support, the loss of ice means the loss of habitat. While phytoplankton in open water can also be productive, they're not a perfect substitute for ice algae. The timing is different. Ice algae bloom earlier, providing food when it's most needed by many species. The location is different. Ice algae are concentrated at the bottom of the ice, in specific areas where they're accessible to grazers. The quality may be different as well, with ice algae having different nutritional profiles than pelagic phytoplankton. A shift from ice algae to open water phytoplankton would restructure the Arctic food web in ways that are still difficult to predict. Indigenous communities in the Arctic, whose cultures and economies have been intertwined with sea ice for thousands of years, face profound challenges as ice declines. Ice is not just a physical feature of the environment for these communities. It's part of their identity, their stories, their traditional knowledge. Hunting practices developed over generations are based on the patterns and behavior of ice. Travel routes across ice connect communities and allow access to resources. The loss of reliable ice coverage disrupts these practices and threatens ways of life. At the same time, the changing Arctic presents opportunities for some. Longer open water seasons could mean expanded fishing grounds. Access to previously unreachable mineral and oil resources could drive economic development. Tourism could increase as the region becomes more accessible. But these opportunities come with costs, environmental, cultural, and social, that must be weighed carefully. In the Antarctic, the future is less certain but no less consequential. The recent rapid declines in sea ice extent have surprised scientists and raised questions about whether the Antarctic is entering a new regime, a state where ice cover will remain persistently lower than historical averages. If so, the implications are significant. Antarctic sea ice plays a crucial role in the formation of Antarctic bottom water, the densest water in the world ocean. This water mass drives part of the global thermohaline circulation, the ocean's conveyor belt that redistributes heat, salt, and nutrients around the planet. A reduction in ice formation, and thus in brine rejection, could slow the formation of bottom water. Modeling studies suggest that under high emissions scenarios, bottom water formation could decline substantially by the end of the century, with potential cascading effects on global ocean circulation and climate. The loss of sea ice around Antarctica also affects ice shelves. Sea ice provides a buffer between the open ocean and the ice shelves, damping waves and limiting the impact of warm water. Without this buffer, ice shelves are more vulnerable to melting from below and to mechanical breakup from waves. The collapse or thinning of ice shelves can in turn affect the glaciers that feed them, potentially accelerating the flow of ice from the Antarctic ice sheet into the ocean and contributing to sea level rise. For Antarctic ecosystems, changes in sea ice could be transformative. Krill, the small crustaceans that are a keystone species in the Southern Ocean food web, depend on ice algae for food during winter and spring. Reductions in ice could lead to declines in krill populations, which would affect everything that eats krill. Penguins, seals, whales, fish. Some penguin species, like the Adelie and emperor penguins, are closely associated with ice and could face significant challenges if ice patterns change. Other species, less dependent on ice, might expand their ranges, leading to shifts in ecosystem structure. But it's important to recognize that the future is not written in stone. The trajectory of sea ice decline depends on human actions, on the choices we make about greenhouse gas emissions, land use, and energy systems. Climate models run multiple scenarios, from those where emissions continue to increase to those where aggressive action is taken to reduce them. In the high emissions scenarios, sea ice declines dramatically. In lower emissions scenarios, the decline is less severe, and some ice is retained even at the end of the century. This means that the future of sea ice is to some extent in human hands. The decisions made in the coming years and decades about climate policy, about transitioning to renewable energy, about protecting ecosystems and supporting vulnerable communities, these decisions will shape not just the polar regions but the entire planet. Sea ice is a bellwether, an early indicator of changes that will eventually affect all of us, no matter how far we live from the poles. And yet, even as we contemplate these large-scale changes, it's worth remembering the resilience of ice and of the life it supports. Sea ice has existed for millions of years, waxing and waning with ice ages and interglacials, retreating and advancing across geological time. The organisms that live in and around ice have survived dramatic changes in the past. They've evolved strategies to cope with variability and extremes. While the current rate of change is faster than anything in the recent geological record, and while many species will face challenges, others may adapt, shift their ranges, or find new niches. The future will not be a simple linear decline. There will be variability, years when ice rebounds, and years when it crashes to new lows. There will be regional differences, with some areas losing ice faster than others. There will be surprises, tipping points where systems shift suddenly from one state to another, and there will be resilience, ecosystems and communities finding ways to persist and adapt. What's certain is that the frozen ocean, as we've known it, is changing. The rhythms that have governed polar seas for so long are being disrupted. The ice is thinner, younger, more fragile, but it's still there, still forming each winter, still playing its role in the climate system and in the ecosystems it supports. And as long as there's ice, there will be algae in brine channels, seals hauling out on floes, polar bears hunting, and communities living their lives in relationship with the frozen sea. The story of sea ice is far from over. It's a story still being written by the physics of water and cold, by the biology of adaptation and survival, by the policies and actions of nations and individuals. It's a story that will affect us all, whether we live in the Arctic or the tropics, on coasts or in mountains, because the ice is connected to everything: climate, oceans, weather, ecosystems, human societies. Understanding this story, caring about its outcome, and acting to influence it for the better, that's the challenge and the opportunity before us. And now, as the stories of ice begin to settle like snow over your thoughts, let yourself drift deeper still into rest. We've journeyed across frozen seas, explored channels too small to see, watched ice form and melt in cycles as old as the poles themselves. We've seen life hidden in brine, windows opening in solid ice, and two frozen worlds spinning through their seasons. You are connected to all of this, you know. The air you breathe has swept over polar ice. The ocean currents that shape the ice also shape the climate where you live. The water in your body has cycled through seas and ice and clouds countless times across the ages. You are part of the same planet, the same system, the same great rhythm of freezing and thawing, darkness and light. Tonight, as the ice grows in silence at the poles, as algae rest in their brine channel homes, as currents flow beneath frozen surfaces, you too can rest. Let the day's weight melt away. Let your breathing slow like the patient formation of ice crystals. Let your mind drift like ice flows on a calm polar sea. The frozen ocean will continue its ancient cycle whether you're awake or asleep. Winter will come, ice will form, spring will arrive, light will return, summer will melt what winter built, and autumn will begin the process again. The rhythm continues, quiet and sure, a heartbeat of ice and water beneath the stars. Sleep well, knowing you've traveled to the coldest seas and back. Dream softly of gentle ice, of crystalline beauty, of life thriving in the frozen world. Good night.